Before we begin at the beginning, as it were, I have realized that in this video I've used the terms local variable and global variable. If you imagine your computer program steps into a function, you declare a variable called x and you say it's real. So you have a statement real x. What the compiler does is it will create 32 bits for that value of x. When the computer program leaves the function, that memory goes out of scope. Effectively, it no longer exists, and what's more, the function is taken off a piece of memory called the function stack, and that no longer exists. That is what is called a local variable. X only exists in that function while that function is being executed and just vanishes. It only exists locally. A global variable is something else. It is declared in a C program outside all of the functions, including the main function, and it is accessible everywhere from every function that the main program calls, every function that those functions call, and so on and so on. It is globally accessible. It only goes out of scope when the entire program has finished executing. Well, here we are back in the hello2 directory. You might remember that in our make file we used gfortran -shared. The -shared bit is what tells it to create a direct linked library. Of course, the GCC compiler collection calls them shared objects. As well as your trusty gfortran manual, you will have downloaded the GCC manual. Here's the GCC manual. In chapter 3, -shared produced a shared object, which can then be linked with other objects to form an executable. The GCC manual is certainly not easy reading, but we could have just looked in our LD help file that we made ages ago, and we'll see the -shared option there, which is also called -b shareable, and it says create a shared library. Well, I suppose you're supposed to know that means a shared object. And now let's get data out of our DLL and our archive. I've changed this to dec so that now the compilers will ignore this line altogether, and it's a GNU compiler. I've introduced a floating point number by this line that declares alpha as real, or a 32-bit float. Here I set it to 4, and now instead of an empty bracket for sub1 fun1, we have an argument list. The argument list consists of just one argument, alpha. If we now look in sub1 now expects an argument, real x. Again, we've changed that to dec instead of GCC, and now it tells you, as it enters sub1, the value of x, it doubles the value of x. It then says it's leaving sub1 with the value of x equals, well, twice what it was before. Fun1, same thing, it now takes the argument x, which is a real 32-bit number, and tells you it's entering and leaving, and in between it doubles the value of x. Of course, it then calls fun2, and here we are in fun2. Again, it tells you that it's entered fun2 and it's leaving fun2. Fun2 takes a single argument x, which is declared to be real, and it's doubled yet again. Well, over on the command line, we've got rid of all of these things, and we've rebuilt our libraries, libhellostat and libhellodyna. Okay, now we've built our two programs, one linking with hellostat and the other one linking with hellodyna DLL, and let's run them. Well, you shouldn't be too surprised at what happens. Starts the main program with alpha equals 4. The number 4 arrives in sub1, x equals 4. It gets doubled to x equals 8, and then after the sub1 call back in the main program, alpha is now 8. Then it calls fun1. We get the old message. It enters fun1 with x equals 8. It then calls fun2. It enters fun2 with x equals 8, but leaves fun2 with x equals 16. Remember, it doubled. And then, before it leaves fun1, it doubles the value of x again. So it's now 32. And then, yes, this is the line. After fun1 call, alpha equals 32. So it's been successful. It sent the value of alpha into sub1. It's equal to 4, passes these variables within the DLL functions and successfully doubles them. And what's more, it passes the data back to hello.f, and it turns out to be the correct value. So the data has got back from the DLL to the calling program, and everything's fine. Well, we can do the same thing for hell DLL, and we can see everything's exactly the same. The DLL has accepted the right value of 4 for the input to sub1, so alpha equals 4 has got into the library correctly. It all behaves quite well within the library functions, and right at the end we're back in the calling program, and alpha is now 32, and all is as it should be. Now we've seen that if we pass data through arguments to the function or the subroutine, then we've got no problems whatsoever. We can get the data in and out of the DLL. Now, many Fortran numerical libraries, LAPACK, ISPACK, LINPACK, and so on, they only pass data as arguments. So we're in the clear with all those. However, other libraries use common blocks. This is pretty old school stuff for some data in some routines. You can see I've got a big boo here, as people really don't like common blocks very much. We'll like them even less when it comes to DLLs. You see, the thing is, you've probably guessed, the reason that I'm doing this, getting data in and out of libraries, is because we will hit some problem somewhere. Well, we certainly will. So I've begun by making a directory hello3, and I've copied everything from hello2 into hello3. That's our starting point, and then I've got rid of all of this stuff with a make clean. Well, we've altered hello.f and our library functions sub1.f and fun1.f and fun2.f to include common blocks. We can imagine that we might have generated documentation for our library which tells us what functions we can call and what the argument lists are, and that's what will happen in any numerical library that you download. And in the documentation it'll tell you whether or not you need to provide data in a common block or not. Here's our common blocks, common, then a block name between 2 slashes, and then an argument list. In this case, an argument list consisting of just one argument. It will tell us what to call these common blocks. We don't get a choice in the name, just as we don't get a choice in the name as sub1 and fun1, but we do get a choice in the name of the actual arguments. So here we are, we've declared our data beta and gamma. Beta is sent to sub1, which has a common block called sub1 block. Gamma is sent to fun1, which, according to our fictitious documentation, has a common block that must be called fun1 block. And here we've initialized beta and gamma. Beta is 1, gamma is 19.5. We've put in some extra write statements to check what happens to beta and gamma. Here we are in sub1. It says common /sub1 block /y, and then real x and y. They're both 32-bit, just as it is in the calling routine, and it just checks out what x and y are as it enters and leaves. Y is incremented by 7.5 before it leaves. Here we are over in fun1. We declare the common block, fun1 block /y, and again we have y is 32-bit. First of all, we call fun2, so nothing's happened to y yet, but when we return from fun2, we increment y by 101. And lastly, here we are in fun2, common /fun1 block /y, again y is 32-bit. Y is incremented by 202 before leaving, and we have a couple of write statements to inform us what x and y are when we enter fun2 and leave fun2. Let's run this through again. I've rebuilt both the static library and the DLL, and I've recompiled DLL and stat. So let's do stat that calls the static archive. Well, if you check through all this lot, you'll see that everything's behaving as it should be, and in the end, after calls to fun1 and fun2, gamma goes from 19.5 to 322. Here we are, enter fun1, enter fun2, leave fun2, leave fun1. So we're back in the main program. Same thing with the call to sub1. After the sub1 call, beta's 8.05, but back in the main routine, it's been incremented by the right amount. But look what happens when we run DLL. Gamma ends up as 19.5. You might remember that gamma starts as 19.5. So nothing's happened to gamma, despite calling fun1, which calls fun2. What happens to beta? Beta, once it's back in the main program, is back to 1. Okay, this should have been x and y are. And what's happened to beta? Well, it enters sub1 with a value of 0, whereas in the main program it had a value of 1. It leaves with a value of 7.05, but once it's back in the main program, its value is back to 1. The values of alpha and beta are behaving completely as local variables, whereas common blocks are supposed to kind of mimic global variables. Fortran doesn't actually have global variables, and common blocks are a way of getting around this. All our variables in the main program passed to common blocks are behaving exactly like local variables. Well, what happens in fun1? It arrives as 0. We've set gamma to be 19.5. So this number here should be 19.5, but it's 0. Again, the 19.5 just hasn't been passed into the library. Okay, the 19.5 is incremented to 202 as it should be, and the funny thing is, when it gets back to fun1 and it's incremented by 101, we get 303. So within the DLL, the common block is passing data between the two functions correctly. So what's happening? Well, we've already said it, but we'll say it again. The data given to the common blocks in the main program remain as if they were local variables, but within the DLL, the data is passed between the common block correctly. We have no problem at all with using common blocks in a static library, but when we call the dynamic library, we have a real problem. The thing is, if we went over to Linux with a shared object library, this all works absolutely fine. There's something strange about the Microsoft implementation of DLLs. The question is, do we give up and just use static libraries, or are we going to be determined to use DLLs and find some kind of workaround for this?